Welcome to this video. We're going to be talking about a technique called tabular integration. And like to think about tabular integration as a technique that will essentially apply integration by parts multiple times. So if you ever need to apply integration by parts more than once, tabular integration is generally an excellent method when applicable. So let's take an example. So let's say we wanted to calculate the integral of x squared e to the x. Well, the first thing we would do is we would choose our u and our dv, which in this case, u would be the polynomial x squared, dv would be e to the x dx. We would differentiate u to get du, so we get 2x dx, and then remember that you integrate dv to find v, well, the integral of e to the x is just e to the x. So after figuring out all of these pieces, we apply the integration by parts formula. Remember that it is u times v, so that's where the x squared e to the x comes from, minus the integral of v du, so the integral of 2x times e to the x dx. Now, notice this new integral here, again, needs an integration by parts because we have decreased the degree of the polynomial from 2 down to 1. We need to go ahead and decrease it by one more degree, and that's where we need to apply integration by parts again. So because we're applying integration by parts multiple times, this is where tabular integration comes into play. So let me show you how tabular integration works, and then afterwards we'll talk about why it works. So first of all, you create a table. You're going to create two columns. The left column is going to be the polynomial, which is x squared. The right column is going to be the exponential in this case. In the polynomial column, you are going to differentiate as many times as you need to until you get to 0. And we know, since we're dealing with a polynomial, that after so many derivatives, it will indeed reach 0. So we have differentiated the left column, in this case, 3 times. We need to integrate the right column the same number of times. Well, the integral of e to the x is just e to the x, so this happens to be simple. So here's our table. Now, how do we put all of this information together to find our antiderivative? Well, we're going to start off by multiplying down the diagonal. So we're going to multiply x squared by e to the x. We're going to multiply 2x by e to the x. And then we're going to multiply 2 by e to the x. And then we are going to add up all of these products, but we're going to alternate the signs in between them. So the first term is always going to be a plus. That's why there's a plus here. And then it's going to be minus, and then it's going to be plus, etc. So if there were further rows of these columns, then it would continue alternating plus, minus, all the way through. And then notice that this is indeed our antiderivative. So both of the integration by parts are sort of incorporated into this table, giving us a cleaner, faster way of applying integration by parts multiple times. Now, why does this tabular integration work? Well, let's go back to our example for a second. If we use or write down all of the work for integration by parts, then we have the u's, the v's, the du's, and the dv's. And notice this first term comes from the product of u times v. So it's almost like we're multiplying down this diagonal. And because the integration by parts formula is positive u times v, that's why it starts off with a plus. And then the integration by parts formula has this minus the integral of v du. Well, when you apply integration by parts a second time, notice you're going to again have u times v, which is the 2x times e to the x. And if you'll recall, that is exactly this second product here in the tabular integration table. So when we when we apply integration by parts the second time, then this second term here, because of the minus the integral of u times v, that's why the second term has a minus associated to it. And then you'll have minus a minus, which turns it into a plus. So this is why the signs alternate in the tabular integration table, because you will have, starting with a plus, and then a minus, and then a minus, and then if you were to do this again, it would be minus a minus, which would turn into another minus afterwards. So that's why the terms happen to be alternating in sign, and why we're multiplying down the diagonal is because that's exactly what happens when you do u times v in the integration by parts formula. So we get the exact same answer if we apply integration by parts as if we used tabular integration. It's just that tabular integration puts all of the information into a nice, concise table. And that's exactly what this table happens to represent. Now, when can you use tabular integration? Well, the idea is you need to have a product of a polynomial times some function you can integrate repeatedly. And as long as you have this type of product that you're finding the antiderivative of, then you can use tabular integration. So in general, it works best when you have a polynomial times either an exponential, a sine or a cosine, or even more generally, when you have e to the kx, or a sine kx, or cosine kx that's being multiplied by some polynomial. Let me go through one more example. In this case, we have a polynomial times a sine term, sine of 2x. Well, because it's a polynomial times a sine term, we are going to create our table for tabular integration. We have this u column. Remember, this is the derivative column. That's the polynomial, so we'll differentiate until we reach 0. And then we need to integrate the exact same number of times. So we need to find each of those antiderivatives. So the antiderivative of the sine of 2x is negative 1/2 cosine 2x. And then the antiderivative of negative 1/2 cosine 2x is negative 1/4 sine 2x, etc., all the way down the table. We will then multiply down the diagonal. So these blue terms will go together, the green terms, the red terms, and the purple terms. And then remember, you alternate signs beginning with a plus. So plus, minus, plus, minus. And keep in mind that this minus and this minus are going to sort of cancel each other off. And that's why we end up getting this plus here. So plus 9x squared minus 4 over 4. But nonetheless, when you multiply down the diagonals, you add the products together, alternating the sign. This is exactly what your antiderivative is going to be, which is a much faster way of finding this integral. So here is that integral written just one more time. And please note that this table that we've created for tabular integration has greatly saved us time and still allowed us to find the correct answer. So, I hope this video is able to help someone. Good luck with tabular integration.